Assalamualaikum. Today I will present our project on a cascade hyperbolic recognition using hybrid feature extraction in subsurface mapping. I'm Dr. Hasima Ali. This is my team. We are from Unimap. Subsurface mapping using ground penetrability radar. GPR has been acknowledged as an effective and efficient technique for imaging the subsurface, such as locating and mapping buried objects. It uses high-frequency electromagnetic wave propagations ranging from 100 MHz to 1 GHz. So it transmits wave into the ground by moving antenna along the surface. GPR has sizable impact in many applications such as landmine detections, mapping and locating buried utilities such as pipe, cable and gas pipeline, inspections of road and bridge structures, forensic investigations, forestry and also the agriculture. So the development of automated cascade hyperbolic recognition using hybrid feature extraction in subsurface mapping has commercial potential in construction-based industry. Although research on GPR has achieved a certain level of success, however, interpreting hyperbolic signature in GPR images of a buried object is still a challenging task because of the complexity of the GPR raw data. So in practical applications, GPR images could be noisy because of the system noise, heterogeneity of the medium itself, and existing of the mutual wave interaction. The objective of this project is to develop cascade hyperbolic recognition system using hybrid feature extraction by means of empirical mode decomposition and wavelet transform in GPR subsurface map. The block diagram shows the framework of the proposed system. It consists of GPR data acquisition, GPR image processing, cascade hybrid feature extraction by means of empirical mode decomposition and wavelet transform. Then we utilize data analysis using ANOVA test before subjected to multi-class SVM classifier. For the experimental setup, it consists of a GPR system, which is antenna, control unit and ground vision software, a sandbox testbed made entirely of wood to avoid signal interference, and soil medium. We use a 6 tons of dry sand in this experiment. In this experiment, 4 samples have been used, which are cubic, cylindrical, disc and spherical as the buried objects. Experiments have been conducted at Department of Non-Destructive Tests, NDT Nuclear Agency Malaysia, in which scanning operation is guided by Authorized Research Officer NDT. A total of 340 images have been collected. In this experiment, the original image is firstly scaled and cropped in a fixed size in order to have uniformity in size is achieved. For cascade hybrid feature extractions, the first one is empirical mode decomposition. Is a method that any complicated data can be decomposed into a finite and often small number of intrinsic mode functions. So in finding intrinsic mode functions, 2 conditions must be satisfied. The first one, in entire signal, the number of extrema and the number of zero crossing must be equal or differ at most by 1. And the second condition is, at any point, the mean value of the envelope defined by local maxima and local minima must be 0. In this framework, the first one locate all the local maxima and local minima for a given signal. Second step is to interpolate between the maxima and minima to obtain upper and lower envelope. Next is to calculate the mean of the envelope, then extract the detail of the signal. So we have to iterate step 1 to 4 on the residue until the detailed signal can be considered as the intrinsic mode function, which is satisfied the 2 conditions as mentioned before. So after that, we iterate step 1 to 5 on the residue signal to obtain all the intrinsic mode function of the signal. Figure shows the result of empirical mode decomposition on GPR images in terms of intrinsic mode function 1, intrinsic mode function 2, intrinsic mode function 3, and also residue for the cubic, cylindrical, disc, and spherical. As observed, the empirical mode decompositions reveal the pattern structure from the finest to coarsest of the original image. Due to nature of EMD, the lower order of IMF exhibit fast oscillations mode, while the higher order IMF exhibit low oscillation modes. For the wavelet transform, it's of advantage of using variable size timescale for different frequency subbands. The wavelet transform analyzes the signal at different resolutions by decomposing it into a coarse approximation and detailed informations. Figure shows the composition of wavelet transform on intrinsic mode function into 4 subbands, which are approximation, horizontal, vertical, and diagonal, for cubic, cylindrical, disc, and spherical. As observed, the hyperbolic pattern reveals subtle changes of temporal variation in low frequency and sharp temporal changes in high frequency. The result shows that the hybrid features of IMF1 and CH1 horizontal coefficient has achieved the highest recognition rate, which is 99.71% using SVM classifier. Table shows the confusion matrix of IMF1 features and wavelet transform CH1 in hyperbolic recognitions. So based on the table, it shows that all the hyperbolic recognition achieve perfect result in cubic, disc, and spherical. As conclusion, this project has presented a cascade hyperbolic recognition using hybrid feature extraction by means empirical mode decomposition and discrete wavelet transform in subsurface mapping. Based on the result obtained, it shows that the IMF1 plus wavelet features CH1 contains significant information that able to discriminate the hyperbolic pattern of different geometrical shapes such as cubic, cylindrical, disc, and spherical. Thus, it shows that a promising result for development of GPR automated system. Acknowledgement and publications. This project is collaboration between UNIMAP and Agency Nuclear Malaysia under MOU agreement.